So in this video, I'd like to do some preliminary problems in Lagrange equations of motion to make sure that you understand the idea. So our Lagrange equations of motion are written as the derivative of the partial of the Lagrangian with respect to the dot. So this is the Lagrange equations of motion that we'll be spending time at. There is a general form of Lagrange equation of motion which I didn't really discuss, but so remember, when we use this form of Lagrange equations of motion, this Lagrangian, right, has no concept of dissipation, energy dissipation. So we can't do systems where energy is being dissipated. So let's do an example of this. Okay, so first example, let's assume that we have a free particle. So in our free particle, we'll assume that we'll calculate L. So T is the kinetic energy, V is the potential energy. It's a free particle, so the potential in this is 0. We'll assume the particle can be defined as a coordinates of x, y, z. And so its momentum, right, or its velocity is given by x dot, y dot, and z dot. So our kinetic energy term, right, for a free particle of mass m is given by 1/2 m x dot squared, the x velocity and the y velocity and the z velocity squared, or the speed squared. So here's our Lagrangian. So we'll start plugging it in and chugging away at our equations. Notice there are three generalized coordinates, x, y, and z. Because there are three generalized coordinates, our basic solution will be, we're expecting three differential equations. Three differential equations of motion. So we'll take the partial of L. So we'll start off with the partial of L with respect to x dot, first equation. And we're getting mx dot. And then we can take the the derivative in time. So you have to remember that these coordinates, x dot, y dot, z dot, right, and x, y, and z are supposed to be independent variables. So this partial derivative, right, that I'm taking, right, assuming that x dot, y dot, z dot, x, y, z are all independent of each other. So the derivative is mx dot, which is mx double dot. We also know that the partial of L with respect to x is equal to 0. There is no L. There is no x coordinate in the Lagrangian of T minus V, kinetic energy minus potential energy. So we have a second order differential equation to solve. I can solve for this, but I want you to notice that one of the first things you should notice is that that's exactly the same as the taking the derivative of d equals 0. This means that x dot is a constant. So we can repeat this for x, y, and z, and you can see there's a symmetry in these equations, right? So we can repeat this calculation exactly the same, and we'll get that the mass times y dot is a constant, and mz dot is a constant. So we have momentum conservation. Now, I didn't really want to emphasize this right now, but we're going to be looking at conservation principles that are coming from the Lagrangian by looking at symmetries in the Lagrangian, but we're not doing it right now. So the main idea that I want to get across is that momentum is conserved, and so if we have a free particle, the particle's momentum is conserved, which means that the momentum at any time is always the same. So it always stays in the same direction or whatever, but it doesn't change momentum. So let's do another example. So Here we had three differential equations coming because we had three generalized coordinates. But let's do another example of a simple pendulum system. Well, actually, no, let's do oops. Assume that we have a spring system attached to a mass. Assume it's frictionless because we can't do any type of friction with this Lagrange equation form. So there is another way of doing Lagrange equation with something called generalized forces, but I didn't discuss it. So we can actually include a form of dissipation into those equations, but not in here. So we can't do any dissipation with this Lagrange equations of motion, these Lagrange equations of motion. So assume there's a constant k, there's a mass m, it's on a frictionless surface, so basically assume that's at equilibrium. I'll always tend to do things at equilibrium. It's just that I didn't want to spend time doing non-equilibrium calculations. So I'll always assume that this mass spring system has reached equilibrium, and then I'm going to shift. Let's assume that we have a coordinate q. And this q is basically the displacement from the equilibrium point. So again, we're going to repeat this process of calculating the Lagrangian L, which is kinetic energy minus the potential energy. The kinetic energy of the system, if q is a generalized coordinates displacement from the equilibrium, so we can take this as 1/2 m q dot squared. The potential energy that's stored, right, in a spring, if you remember, right, we derived it as 1/2 k the displacement squared. So that just reduces to 1/2 k q squared. So again, we have one generalized coordinate q, which means that we are getting one differential equation from the Lagrange equations of motion. So let's go through the process of calculating. It's a repeated process. The main thing you should learn is that we can take a system. So we're going to see this over and over again, and we're going to take a system, we're going to construct the Lagrangian, plug in the Lagrange equations of motion, and then solve the equation of motion for the actual motion. But once we get these differential equations, right, of second order, then we have actually solved the system. So we might not be able to algebraically solve these differential equations, but at least we can plug into a computer and numerically solve these equations. So q dot. So here is q dot. So the q is the generalized coordinates. Again, we'll get mq dot, and I'll put a little double bar there. So the first term over here is the derivative of the partial of L with respect to q dot. And remember, we're assuming q dots and q's are independent variables. So the derivative, right, then becomes mq double dot. Now we're going to repeat the process for process of the partial of the Lagrangian with respect to q. And if you look, it's the 2 comes down, we get a kq minus. So this minus this is equal to the differential equation of motion. So we get a bar here. So this is mq double dot minus minus, which is plus kq. And we divide by m if you want. And there. And if you remember, this is the generalized form of a second order differential equation with linear homogeneous coefficients. And so we know that we call these terms omega O squared. And we've done this calculation before in terms of Newtonian mechanics, but in terms of Newtonian mechanics, we have to do a lot of work using the second law and stating sigma f and calculating the forces and stuff. And so here it's a very mechanical process. Lagrange equations of motion takes a system. So this equation, Lagrange equation of motion, takes a system, right, that's non-dissipative in energy, and basically we can just write the Lagrangian, and after we get the Lagrangian, plug these values into get a second order differential equation in the number of generalized variables, solve the differential equations we have. So these are the equations of motion. So this is the first equations of motion of the system. I'll just call it EOM, equations of motion. So in this case, it's a single equation of motion. We know the solution. It's a we know that we can find the basis vectors, expand the basis vectors to sine and cosine of omega OT. And once we've done that, we have the full solution of what Q is. So let's do another example. Let's make it a little more complicated. So again, this is a mechanical process. So we're trying to do this so that we can construct mechanics in terms of Lagrange equations of motion. So in the next example, let's take a pendulum. So here is our pendulum. We'll assume it's a mass m, a length of a string, and assume it's not oscillating or something, just this fixed straight length of string, theta. And we have that this mass moves back and forth. Okay, so if we know this, right, let's go and calculate the Lagrangian. So here's our system. We are told the string hanging off a ceiling, and this mass oscillates back and forth, and well, we know generally what it looks like. So we're going to calculate the Lagrangian. So let's do the L over here. It's actually T minus V again, kinetic energy. So if you think about what the kinetic energy is, so if this L, right, and the rate of the velocity, right, is given by L theta dot. So our kinetic energy is nothing more than 1/2 mass times the length L squared. That's your kinetic energy. So that's the tangential velocity L theta dot. Once we have that, right, we have the potential energy, and let's make it simple on ourselves. We'll say that, so if you remember, this is the height L, and then this is the component of L after it swings theta, right? This component is given by L cosine of theta. So the height difference of the elevation from our 0 point with potential energy would be L minus L cosine theta. So mg times L minus L cosine of theta. And this is the Lagrangian. Oh, actually I just noticed that this L right and that L kind of look exactly the same, so maybe I'll switch this to a lowercase l. I just didn't notice it, I'm sorry. So let's change this to a lowercase l so that you don't get confused with the L's. Okay, so we can rewrite this so you can get this just to make sure that we don't have any questions about derivatives and great. So here's our equations of motion. Again, we're going to calculate let's do it over here. I think there's enough space. L theta dot. So this is the first term. So the Lagrange in respect to theta dot, we're getting ml squared. The 2 comes down, theta dot. Okay, and what is the derivative with respect to time of the partial of L with respect to theta dot? We get ml squared theta double dot, second derivative. So we're using, anyway, so the next step, right, is we have to calculate the partial of L with respect to theta. So all these are 0, 0, and then we have the derivative cosine is minus sine, so we get minus mgl sine of theta. And so this term minus that term gives me the full equations of motion. So our equations of motion are ml squared theta dot minus minus, which becomes a plus, mgl sine of theta is equal to 0. Now you might notice that we can divide by m. So this is the equations of motion, but we can probably reduce this. No, we can't reduce this. So here is the equations of motion. Okay, nothing exaggerated, just looking at ml squared theta dot. Let's divide by ml squared so the m's cancel and we get the following. So we get theta double dot plus L, G over L theta is equal to 0. And again, it looks like a periodic motion, and I made a mistake, I'm sorry. So it's theta double dot plus G over L sine of theta is equal to 0. This is not an algebraic equation that we can solve. This is from experience. We don't know how to exactly solve this equation. Because, anyway, it's not solvable. But if we assume that theta is in radians, if theta is in radians, and theta is, let's say, smaller than about 15 degrees, where then you can say that sine of theta and theta, where theta is less than 15 degrees, but it's in radians, of course, it's 15, so I don't want to convert 15 degrees into radians, approximately, then this differential equation approximately gives us a new equation that looks like plus G over L theta is equal to 0. Again, we see a second order differential equation in our standard form, and we know that we called this before omega O squared. So for small oscillations, we're expecting that the angular frequency is the square root of G over L. So the system is oscillatory, and it's offering a simple harmonic motion when theta is very small. So the angle, this angle, if it's less than about 15 degrees or so, then sine theta approximately to 2 or 3 significant digits, right, is the same as theta and sine theta are equivalent to each other. So we get this oscillatory motion of the square root of G over L. So it's a mechanical process. You're going to do this over and over again. So let me do some more examples. Let's make a double spring system and go through the process of doing a double spring system. So we'll assume that we have a wall frictionless surface, we have a mass M1 attached to a spring constant K1, another spring constant K2, and this system, right, I'll assume it's reached equilibrium, and we'll call Q the displacement from the equilibrium. So we pull it, and then we let go, and we assume there's some kind of oscillations. What exactly is the frequency oscillations? If assuming it's a frictionless surface, because remember these equations are for non-dissipative systems, that equation right here, Lagrange equations of motion. So again, we type L, T minus V. What is the kinetic energy? 1/2 m of Q dot squared. What's the potential energy? The potential energy that's stored in each spring is 1/2 K1 Q squared plus 1/2 K2 for the second spring Q squared. So you should be able to write these Lagrangian very quickly. You don't have to kill yourself, but it's a very mechanical process to repeat this over and over again. I'll reduce this a little bit so that we don't waste time calculating these things. I'll factor out, so there's a minus 1/2 K1 plus K2 Q squared. And if you noticed, right, this system seems to be equivalent to another system that we just did earlier, where we had a single spring and with attached to a mass and a frictional surface. And it's basically the new spring, right? So we can take this system and convert it to a new system that basically consists of a spring mass M1 with a spring constant of K1 plus K2. So the same idea of taking a double spring system is actually a single spring system K1. We can actually do the calculation. I can repeat this calculation, and we'll find that I won't go through it because I'll pick another problem just to make sure you're understanding this idea. And so mq dot minus 1/2 K1 plus K2 is Q squared. So our general solution for this, right, was of the form of q double dot plus omega O squared q is equal to 0, where we get k over m, so it's k1. So the general solution, if you go through it, right, it's from earlier, so hopefully you kind of look over the video again. We can actually go through the process, you'll get the same equations, and we're basically get omega squared is k1 plus k2 over m. Anyway, so let's do something more complicated. Let's do a coupled system here. So in the coupled system model, right, I'm going to take a system, and it's a little more work. We have a spring attached to a mass m1. Here is k1. Here is k2, a spring that's attached to another mass m2 attached to another spring, k3. So we have two masses, three springs attaching between them. And I'm going to assume that they've all reached equilibrium, and that the displacement of one is called x, the displacement of the second from equilibrium is equal to y. And so again, we're going to calculate the Lagrangian L, T minus V. What's the kinetic energy of this? We're assuming that M1 and M2 only is the kinetic energy. So that would be 1/2 M x dot squared, M1, plus M2 y dot squared, minus now the potential energy terms. So this is the kinetic energy that's stored in each of these two masses. The potential energy, right, is, well, if this gets displaced by x, this string gets stretched from equilibrium, so the potential energy in that stretch from equilibrium point, right, is given by 1/2 k1 x squared. I can repeat this again. If this thing is squeezed from equilibrium, the potential energy that's different from the equilibrium, right, is given by, for this spring, is 1/2 k3 y squared, plus, now I have to look at the energy stored in this spring, k2. Now, if x and y were the same value, if everything shifted by, let's say, 1 meter or 1 centimeter, right, across, then this spring would not stretch. There would be no potential energy stored in that extra spring from equilibrium. But if this was changed to 1 centimeter and y was 0, then this would be squeezed by 1 centimeter. And if this was 0 and this is 1 centimeter, then this would be stretched by 1 centimeter. So the idea is that this spring, right, is being stretched by the difference. So the energy stored in that spring is k2 x minus y squared. And I'll actually try to reduce this a little bit so that we get these terms out of the way. So I'll write this as 1/2 m1 x dot squared plus 1/2 m2 y dot squared. And there's an x squared here. There'll be an x squared coming in here, the 1/2. So I'm going to absorb that into 1/2 of k1 plus k2 x squared. Now there's a y squared term coming in here from k2, and there's a k3 over here. So I'll absorb that into 1/2 k3 plus k2 y squared. Eventually, right, there's leftover, so we've taken care of these three terms, product, and then there is an xy term right over here that if you take minus, oops, this is a minus here, then there is a minus cancels to a plus, and you're left with k2xy. The 2 would cancel the kxy. And anyway, so it's a simple form, so it can actually calculate very quickly the equations of motion. So let's calculate. How many equations of motion am I getting? I should be getting 2 equations because there's 2 generalized coordinates, x and y. So we're looking at 2 differential set of equations. So let's go through the partial of L with respect to x dot. And again, you're going to get m1 times x dot and then we take the derivative of this term, which is m1x dot, to get this term, and that is m1x double dot. And now I have to calculate the partial of L with respect to x. So the Lagrange with respect to x, 0, 0, this will be 0, but there's a term here, so we're expecting a k1 plus k2 minus x plus k2y. And so we can say that this term minus this term, right, is equal to 0. And so we get m1 x double dot minus becomes a k1 plus k2 x minus k2y is equal to 0. So here is our first equation of motion for the differential motion. So remember, this is a second order differential equation, but it's coupling a y. Our second equation, we can repeat this whole process over again, and I won't go through it because it's symmetrical, so we should just analyze this in terms of symmetry. X's and Y's are exactly the same, we just have to swap the values of K3 for K1. So where would we be? So we'd get M2 Y double dot plus, there's a K2 here and there's a K3 here, so we're expecting a K2 plus K3 times a Y minus K2Y, so we're expecting K2 to be the same, so it'll be K2 at 0. So by symmetry you can analyze this, but you should go through the process of double checking by doing this calculation over again. Verify everything, because I do make a lot of mistakes. Here is the second equation of motion. So we have a system of equations, two systems of equations. It's a second order differential equation, so if you take your standard ODE class, right, they'll show you how the mechanism, how to solve it. But of course, we'll be solving this, right? And our idea of solving this is in terms of converting this into a matrix form. So let me show you how to do this, because so it's not important for us to solve this equation right now at this point in time. The emphasis that I want to make sure you can do is basically take a system, whatever the system is, and convert it into a Lagrangian, and then plug them into a Lagrange equations of motion and get second order differential equations. Here are the equations of motion, two of them. So once we get up to here, right, I'm happy that you've gotten up to this point. Okay, so here's our system of equations. So let me show you what our intent. So in a couple of weeks we'll be redoing these problems, right, but we'll actually be trying to solve them. And the idea behind it, right, is we're going to convert these into matrix forms. And this leads into ideas in quantum mechanics. So the idea is that I'm going to create, let's say this is phi. I'm going to call phi this matrix called X and Y. So what you want to do is we want to say that the second derivative in time of this ket is given by, well, actually I'll do it exactly this way so we don't get any understanding of what's happening. There's a matrix. Actually, let me change this to X and Y. And just to create more space, a bigger matrix, more space. Here is X and Y is equal to 0. So the first term is K1 plus K2. And actually, I'll divide by M1 across here. And so I will divide by M1 and then over M1 over here and M2 over here. So I'm actually doing a couple of things in one step. So take this first second order differential equation, divide by M1. So we'll get M1 K2 over M1 acting on X. And then there's a minus K2 over m1. So this is minus k2 over m1. And then the next equation, right, the coefficient is going to be minus k2 over m2 and there is a component of k2 plus k3 over m2. So we've taken our second order differential equation and converted it into a matrix form, and later our notation, right, I like to be using is that I'd like to say column vectors are kets. So this is, so we can call this matrix A, and so this is the second order derivative and plus this matrix, let's call it A, times the ket psi is equal to 0. So when I start explaining how to do diagonalizations with bras and kets, there's a nice notation that using Dirac notation, it's very, you can remember it quite well by using Dirac notation. But anyway, so our intent is it's not really important right now to solve this equation. In about 2 weeks or so, we're going to be actually solving these types of equations by diagonalization of this matrix, the matrix A. But you can actually kind of see, kind of starts looking like something that you see in quantum mechanics. So later, right? Anyway, but it's not quantum mechanics, not yet. We have to do the Hamiltonian formulation of mechanics first.